This is loud. Hello, Bucharest. Thank you. So thank you for coming. I'm going to be talking today about flow, specifically the flow of work through the systems in which we work, the organizations, the teams building software. But I like this quote. I'm not going to talk about AI much. There is a bit at the end about not Gen AI, some other form of AI called agent-based models. But I like this quote from one of my favorite British authors. He's a science fiction author. He sort of used to write near future science fiction, but he had to stop because everything he was writing kept coming true. So Charlie Stross, great author, and he has this lovely idea, or maybe terrifying idea, that's quite relevant to what I'll be talking about today, which is that artificial general intelligence is already here. We just call them companies, and we work in them executing their algorithms very, very slowly. In some ways, this is quite a depressing talk. Sorry, because what I'll be talking about is the fact that as knowledge workers, what we do is take stuff, information of some form. Maybe it's a user story and you're an analyst or QA and you write acceptance criteria. The user story becomes more valuable as you add more information to it. And then a developer will pick up a user story. They'll write some code. The code is more valuable than the requirement. And then finally, something goes into production and it's the most valuable thing, which is running working software. It's why the Agile Manifesto prioritizes working software. But what I'll be talking about is how that world of work is actually very similar to lots of other systems that we participate in. Whether that's manufacturing, whether that's supply chains. Essentially what we're doing is taking a thing, making it more valuable. Right? We have an inbox with a thing coming into it, we pick it up, we make it more valuable and put it to the next outbox, and then someone will pick that up and make it more valuable. In the same way that raw materials get turned into cars, right? You get a bunch of metals, raw metals, which are progressively turned into more valuable widgets, and then those widgets are turned into wheels, and then finally you get the car, which is the valuable bit at the other end. Or oranges from Seville. They're on the trees, and then they get through a series of value-adding stages, if you like, into a store where you can purchase them. So these value streams, these streams of activities that we participate in daily, whether that's writing code, testing code, whether that's defining requirements, whether that's participating in architecture forums, this work is all about taking some form of information and adding more context and making it more valuable. Now, my hypothesis is that we don't have time, mostly in our day jobs, to sit and think and model how work works, how the flow of work through our systems actually happens. Right? And we don't have time to optimize this flow of work often. It's often why you hire people like me. I'm a consultant, I work for a consultancy, so you hire me to come in and have a look at how we can improve the flow, how we can become more productive, developer productivity, woo, for the win. You can't measure it, incidentally. That's just a throwaway from Martin, contractually obliged to say that from a thought worker. So it's about how we can take a step back and use some tools to understand the world in which we work, the world in which we live for many of our waking hours. So, and those are the companies that we're executing those algorithms in. That's the system. We're executing these algorithms slowly compared to a computer doing it. So it's called How Flow Works and Other Curiosities. Now the reason is I can never keep my mind on a single thing. I'm not a great computer finisher. My brain goes in all different directions, and so I couldn't limit it just to flow. I had to put some other stuff in there, like why we should nuke integrated single integration environments from Orbit, and what Lego do to improve productivity. So I've got some stuff, but I should explain, this is the culmination, if you like, of a journey I've personally been on since about 2016-17, when I first started getting really interested in lean product development, really interested in the economics of what makes the stuff we do work. Right? and how we can optimize those economics to make us go faster, to produce better quality, and so on. So flow works and other curiosities. I'll ask this question at the start, and we'll come back to it at the end. If you were in charge of Lego, in charge of making Lego sets and building them, children building them, or adults like me, I'm an adult friend of Lego. If you were in charge of that, how would you make it more effective? What changes could you make to building Lego that would improve the experience and let you go faster? So have a think on that as I talk through the rest of this. So I'm going to start off by introducing myself. I did this some time ago, sorry. I have to apologize for microservices. I'm one of 3 people who can claim to have invented them. So I invented microservices with Martin Fowler, along with Adrian Cockcroft and another guy, Fred George. So I wrote a thing 10 years ago, 10 plus years ago. Would you believe it's over 10 years? And I've also written another thing more recently for Martin on legacy displacements, how we can take our big legacy code bases and migrate them gradually away to more modern software. And I actually wrote that with my former colleague, or 2 former colleagues, one of whom is actually here as well, from a company called Softwire. That's Ian Cartwright. I'm not sure if he's in the room or not, but you can look him up. He's around. He's awesome. He taught me everything I know. He didn't teach me everything he knows, which is annoying, because he knows a lot, but I learned everything I know from him. So that's me, and work for ThoughtWorks, blah, 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 do stuff. Now, work flows as information through value streams, or why shared test environments should be nuked from orbit. What do I mean by this? These words are picked specifically. Work, the stuff that we do day to day, writing code, running tests, elucidating requirements, writing business requirements documents, decisions about architecture, all these things we do, and not just limited to software, but all knowledge work, right? So lawyers are participating, they've got the same thing, they've got contracts, information that they have to check, make them more valuable, they become signed, enforceable. All of us participating in knowledge work, we have this process where something that's less valuable gets turned into something that's more valuable, passing through something called a value stream. Now, who's come across value streams before? Not many of you. That's great. Unless you're all really nervous and don't want to admit it. So if you do know what value streams are and aren't telling me, this could be really boring. But otherwise, hopefully, it'll be interesting. So this is what a value stream from Lean looks like. And on here, we can see a number of things. I'll step back a bit so I'm not blocking it entirely. So you've got a series of value-adding activities at the top, right? In this case, it's 3 days, 1.5 days, and half a day each of these activities is taking. And you've got a series of wait times down the bottom. This is stuff that's sitting in between value-adding activities, right? And this is from a real project team some years ago. This is a software development lifecycle from a real project team I was working with as a consultant. And you can look at this as, on average, a user story took 3 days to develop. It waited 2 days in a backlog on average. Took on average 3 days to develop, on average 1.5 days to test, on average half a day to deploy, right? But after development, it sat waiting in a queue for 10 days, doing nothing, earning no money. There's no value being accrued by this. It's sitting there waiting for something else to happen to it, right? This is inventory. Stuff sitting in queues is inventory, right? If you're in manufacturing, we know that inventory is bad. Inventory acts as a drag on your balance sheet. It costs you money, whether to store it or to buy it too far in advance of actually using it or whatever. It's the same with what we do. Stuff sitting around waiting, earning money is inventory. Now, why do I say it's a drag on the balance sheet? Well, things happen while stuff is sitting around waiting for other things to happen. Requirements change, right? Maybe there's a user story sitting around waiting for 10 days that is no longer needed, right? And you've spent all that work, all that time and effort building it, but you're never going to actually use it, right? So this is inventory, stuff sitting around waiting for testing, and then 30 days on average waiting before it's deployed, which is when you start earning money or bananas or save lives or whatever it is the software is doing for you, okay? So what I'm saying here is this is defined in terms a little bit. This is the value creating time or the cycle time of the activity. You've then got wait times over here, which is the bottom bit, and then you've got the production lead time, which is the time it takes to go from end to end. So if you're in this team, when you start on a piece of work as a developer, it takes you on average 3 days, up to 6 days, right? That's the average 6 days, that average 3 days. You're gonna wait 47 days before that work hits production, right? This is a classic example of value stream and value stream mapping the systems in which we work, right? Understanding how all the stuff that we do fits together as a whole. Right? Because once we start to understand this, we can start to optimize. Because immediately, I'm sure the smart people in this room, you could immediately start to think about other things we could do other than wait 30 days on average before deploying. Maybe we could double the amount of times we deploy every month. But this is a 2-month release train, 30 days on average. Maybe we could deploy once a month instead of once every 2 months. Now it would be 15 days. And we've doubled throughput by doing nothing else than cutting down these wait times. Managers like doubling throughput. That's a good thing. What did you do this week? I doubled our throughput. Good stuff. No one's ever going to say bad stuff to that, right? Now, as I say, in this we've got a total waiting time of 42 days, value-adding activities of 5 days, and it takes, therefore, 47 days to go from the start of the funnel into deployed code, earning money. This is a simple one. I'm sure many of you work in large organizations. This is another example of a value stream map from a bigger organization. It's about a 200-year-old organization, this. You don't need to be able to read it. The point is, it's really long, right? We got bored actually trying to understand how long this stuff took once we'd identified some like few bits in it. So this is on average 1 to 3 days happening here. No, 1 to 2 weeks happening there, 3 to 5 days there. So what we have on here is this side. This is something called the fuzzy front end. Right? This is all the stuff that happens before work hits your teams. Right? So it's Don Wanetson's fuzzy front end. You've got work happening in the middle, developers writing code and testing. In fact, that blue card there is writing code. And that's testing. And then all of this up here is integration testing, is QA, is regression testing, is handover to operations teams. Right? So now when you think about how long it takes for a piece of work to go through that value stream, it's months, if not years. And it takes, on average, 3 days to write the code. In fact, it could be infinitely fast writing code here, right? The code could just be written like that. Hey, maybe there's a tool we could use that has just been invented to help us write code a lot faster, allegedly. Gen AI, right? Great, Gen AI is going to help us write that bit of code really, really quickly. Guess what? That's a minor effect on the overall value stream. The fuzzy front end is months, 6 plus. This is 3 months worth of testing. You could write code infinitely fast, and you're still not going to see your impact of that work for months, if not years. So this is an interesting thing about Gen AI and how it, how it participates in not just the writing code part of the software development lifecycle, but everything else. Because what we're going to do if we get this much faster, the writing code bit, is shift the constraint elsewhere. We'll have more code to deploy. We better get good at deploying. Right? We're going to have more ideas that we can implement. We better get good at generating ideas and turning them into requirements and things. Right, so that's a more complicated value stream. There's some icons on here. One is coordination. These are the different types of wait time we see in companies, on teams, as work is flowing through these streams. So coordination is when you're waiting for one or more other team, right, to get stuff done. Right, so I can't do this thing because I'm waiting on this team to develop, to add a field to an API before I can now integrate with that team again. Those sorts of things, right? That's coordination. We then got scheduling or cadence, meetings typically. This is the sort of thing I'm talking about with schedules. Architecture review boards, who's got one of those? Right? That's something that happens on a schedule, right? Or change request boards, these sorts of things happening on a schedule. And we have these things in here. In fact, what we have in here is a bunch of solution architects who are, they get sort of ideas for solutions and they develop options for how to implement it, and they only meet every couple of weeks to decide how they're going to do that. So it's kind of like a review board, architecture review board. Now, fun fact from Accelerate, every time you have change request boards or architecture review boards, it predicts low organizational performance. And I use that in the technical sense of predict, the statistical sense. If you have these bodies in your company, then it predicts you'll be in the low-performing group of companies in the research they did. And it's because as work is flowing through these value streams, they hit these points and stop. And say the architects only meet every 4 weeks to make a decision about a thing, that work is blocked for 4 weeks. Right? So scheduling, and then we've got synchronization. And the thing with scheduling, I mean, there's an interesting thing with scheduling. If you have twice as many meetings, you also double throughput. So there you go, meet twice as often. Obviously, you don't meet every day, maybe that's too much. But you can double throughput in interesting ways. You also have queues of work sitting around. This is the inventory I was talking about. This is queues of requirements that haven't been developed yet, or analysts haven't sort of fully worked on them and turned them into epics or user stories or whatever. This is code that's sitting around waiting to be tested, or stories sitting around in queues waiting to be developed, or stuff in a release train waiting for the next time the train comes to the platform to get on. And this is, in any of our value streams, we'll have all these queues everywhere. Jira, backlogs, they're queues. That's inventory you're holding. The classic thing I see a lot of, is you have like a Jira backlog. It'll have like 2,000 items in it. And you only have to work on the top 5, right? And the other 1,995 are just sitting there doing nothing, right? Delete them, that's my advice. Get rid of them, you're never going to build them. And also, the thing with that is, it hides the true state of the system. If you've got a ton of stuff in a queue sitting around waiting that you're never going to build, you don't actually know the true state, how truly things flow through your system, through the queues. So we've got a bunch of queues here waiting for options, waiting for the integration team, and so on. Sometimes we get all 3, sometimes we get all 3 at once. And this is why we need to nuke single integration environments from orbit. Shared test environments, you have all 3 conditions often. So you have to wait on another team who are using it before you. Maybe you have to wait on another team or 2 other teams because they need to deploy their new versions of their software. Maybe you have to wait on a schedule because you can only use it 6 weeks in advance from now. You have to book some time. Right. Now, this is a fun thing about the economics of this. Why do companies still persist in having single integration test environments? So the excuse I often hear is something like, oh, we can't afford another one of X, right? So we were using SAP HANA, we can't afford another license for SAP because it's really expensive. So we're just going to have a single integration test environment with SAP in it, and everyone will have to use that. Now, of course, the economics just don't work, just don't make sense. Say you have to spend another $1 million, million euros, whatever it is, on a new environment, a new license. Let's say $1 million, round number. And if you've got 10 teams all sitting around waiting to test their software, just sitting around waiting for that software to go into the integration test environment, that software is sitting around not making money, right? The new features aren't making you any money. It doesn't take very long for those teams waiting around to be well over $1 million, actually, in value that's not been delivered. The opportunity cost of these things is huge. So there you go. If you sort of think about the economics in that sense, if you think about the fact there's a queue of a ton of people, expensive, well-paid, highly skilled people who've written this code, and it's just sitting there not earning you money because you haven't got more than one integration test environment. Think about the economics. It's basically what I'm saying. So life moves pretty fast. I'm going to do a little bit on queuing theory now. I hope you don't mind, because it's a software conference, so I thought let's talk about it. Everyone knows queuing theory from one person. Florian does. Excellent. Good job. That's another one. Excellent. Good. Well, hopefully you'll know a bit more about queuing theory in a minute. Bits of it. Good. So messaging, right? Event-driven architectures are a thing. Kafka is a thing. RabbitMQ is a thing. SNS and SQS are things that exist that offer queues and message queues, right? You produce messages in your software, you put it into one of these things. Other bits of software process these messages, whether you're using lambdas, whether you're using microservices, whatever. So, and queuing theory relates to how these systems behave. But it also relates to how any system with queue behaves, like the world we work in, where we've got all these queues. So there's some interesting parallels we can draw. Life moves pretty fast if you don't stop and look around, blah, blah, blah. Okay, so I like to imagine this as there's a CIO, and he's reading Computer Weekly online, or Computer or Retail Weekly or something, and he sort of says, I've just heard about this thing called a platform or platform engineering. Apparently you get a DevOps with it, and the developer's like, yeah, okay, sure, let's have one of those. So what is it about platforms that have sort of eaten the world? Because everywhere I go, everyone's talking about platforms and platform engineering, right? We need a developer experience platform. We need a business platform. We need a platform to help us go faster, right? We need to host our business capabilities for reuse on a platform. Why is it, and what characteristics of platforms make them so useful? And what is it about how we build them often that is so wrong? I'll explain this using queues. So this is the reason IaaS platforms are MMC queues where C tends to infinity. I'm going to explain this. I'm going to explain these terms. It's basically why self-service platforms are the way to go. Right? And if you don't have a self-service platform, if you're putting too many barriers in the way of your developers using a platform via self-service, you're missing a trick, because this is how to go really, really fast. This is why we're building platforms all wrong. So in terms of queuing theory, what we have is a queue. Maybe that's Jira, or maybe that's a Kafka, a queue in Kafka. So we have queues, and then we have producers pushing stuff into the queue. That could be an analyst who's finished working up their user story, put it into Jira, or it could be a message being put onto a queue. We've got service nodes which process messages on the queue, and then you've got departures where you've got the rate at which those service nodes can process the messages, gets them off the queue. And that's basically that sort of notation that I was talking about, where we have a distribution of messages coming in here, which is the MM bit, and the number, or C, refers to the number of service nodes. So if you think about a supermarket, when you've got a big queue of people waiting to pay for their food, that's an MM1 queue, because you've got a single person who's processing your groceries, right? MM1 queue. Same with an airport. When you're trying to check in at an airport, it's an MM1 queue. We then have C queues, MMC. This is where C is the total number of nodes, total number of service nodes processing. So this is, say, competing consumer pattern in messaging, which is when you have more than one consumer all trying to read messages off the same queue. Now that's all very well, James. Thanks for that. What does that have to do with platforms, the world of work, and going fast? Well, because you can look at traditional ops teams, we can look at how operations and platforms works through this lens. Now, a traditional operations team is essentially an MMC queue, where C is the number of expensive, highly paid people you can hire to process the requests of your developers or the rest of the organization. Right, so you've got your ServiceNow thing, right? And as a developer, I would need a new VM. I'll log a ServiceNow ticket. And there's some lovely DBA somewhere who's going to create my new database, or sysadmin created my VM. But the rate at which those requests can be satisfied is limited by the number of these people you can hire, right? And as I say, they're expensive. They're highly skilled. There's not many of them around. And if you've got fewer of those than you've got of requests, then things take a long time, right? That's the first thing. Then we have this, oh, sorry, a bit of a swear there, the sort of broken private cloud, right? So this is where we put a nice GUI on top of the ops team and call it a platform, right? You know you've got one of these. There's some people smiling down the front. You know you've got one of these. Well, the signal is if it took 3 months to get a VM before, and then you get your new private cloud, and it still takes 3 months, this is what you've got, right? Because you're still scaling by the number of people you can hire, the highly skilled, highly paid people, right? That's the rate at which you can process the request to create stuff. Now, the reason AWS, the reason cloud native, the reason infrastructure as a service is a thing is it flips this equation. Suddenly, you can process requests to do stuff at the rate at which the hypervisor can process them, essentially. It's dependent on computer hardware, not on expensive people. It's dependent on the infrastructure of the cloud provider. That's why self-service is such a force multiplier for developers, for getting stuff done, improving the rate at which we can do stuff. Then you've got, you've got the naive platform, which is the worst of all possible worlds. We see this in the wild quite a lot now, where you think, we're going to have this platform, we've got a platform engineering team. So you put the platform engineering team over your nice self-service private cloud, and you have to scale by the number of people in your platform team because they're processing the requests for your private cloud. So this is when you build a platform, but you don't offer capabilities on the platform as self-service. Oh, we're going to have I don't know, I need a new Kubernetes cluster, right? So that's great, you can have a new Kubernetes cluster, but you have to wait for the platform team to build and configure the Kubernetes cluster on AWS underneath. And again, this is sort of putting barriers of expensive, well-paid, highly skilled people over the thing that gives you the benefit, which is self-service, access to infrastructure. So if you're not providing self-service access in your environment, you're missing a trick in terms of throughput, because the other three models are expensive and slow, fundamentally. It scales by people, right, in terms of queuing theory. C is the number of people, whereas infrastructure as a service or self-service access to platform infrastructure, I can stand up my own build pipelines, I can stand up my own observability frameworks and dashboards. If I can do it myself, it gets other people out of the way, out of that value chain, and is faster. I'm just going to flash this because Neil Ford's in the room and I like an animation. He taught me everything I know about animations. Unfortunately, not everything he knows, which is, again, unfortunate. I keep being taught by all these amazing people, but they never tell me everything. So that's expensive and slow, flash it, and this is why self-service is, that's why AWS is the thing. The rest of it is expensive and slow. This is a former colleague, he wrote at length about this in what I talk about when I talk about platforms, about how self-service is the thing that makes the economics of platforms work. This is the second part of this cartoon. Just heard about this thing called a platform. Okay, boss, we've got a DevOps, but we're still taking 2 years to get anything done. Because we fall into the trap of constraining our development teams, in terms of access to the infrastructure, the services that they need from our platforms. Now, quick sidebar. On generative science. Now, generative science is interesting. It's a type of science where you look and try and model the world, right? And by modeling the world, you can ask the model questions and then translate the results potentially to answers in the real world. So this, for example, if you were going to go to, I don't know, Mars, the Curiosity rover on Mars, they can't run lots of experiments by sending lots of Curiosity rovers to Mars. It's too expensive. So they build simulations, models in the real world here, run the models, learn about what works, what doesn't, and then apply those via engineering practices to the thing that actually goes to Mars. And hopefully you de-risk everything well. That's generative science. The study of complexity is all about using models and simulations to understand more about the real world by playing with the models. Because the great thing about models is you can turn time up, right? The problem with what we do often is time turns out you can't accelerate time, really. You can't say I want to move twice as fast and see the results of this change I just made on our teams. But with models, you can. Models, you can double the clock, if you like, double the rate at which you can find stuff out. So it's a very efficient way of understanding the world. Now, here's an example of a model, simple model. This is in a tool called NetLogo. If you've come across Logo, it's a tool for teaching kids to code. This is NetLogo, which is multi-turtle logo. They're called turtles, these little things. And you can use this tool to do all sorts of interesting models, right? So a lot of complexity science is done through models in NetLogo, would you believe? This is a model of birds flocking behavior. And there's a few parameters in here which you can set, and it's like how far they get to one another, the distance they can see, how quickly they can turn, the rate at how fast they can go. And what you can see here is, well, they're not flocking. It's Brownian motion, right? Because the parameters have been set to the point where you get this Brownian motion behavior. But if you fiddle with some of these parameters, the system undergoes a phase shift, right? A phase transition into a new state, where very quickly you see in the model you get this beautiful sort of emergent flocking behavior. And this is how real sort of things like studies about the Amazon rainforest and predators versus prey and all this stuff, lots of sociology is done using this as well. Here's another example. This is virus spread in a population. So again, this is based on the distance that people get to one another. A few simple parameters over there, and the rate at which the virus you become immune to the virus and so on. Funnily enough, this was actually used in anger for COVID modeling. So I'm not sure about it in Romania, but in the UK we had this like 2-meter rule, and you have to wear masks in groups over 5 people. That's done using these sorts of models, because you can put the parameters in, you can run the model. Does it look like the real world, the real spread of COVID? Yes, cool. What happens if we stop the people getting close to one another? The virus stops spreading so fast. So, you can do genuinely interesting things with this. We actually built in ThoughtWorks in partnership with the university in India a tool called EpiRust, which basically modeled all of Mumbai and the surrounding environment. Tens and tens of millions of people or agents in the model. And that was used to issue advice from the government in India, in Mumbai. So you can do interesting stuff with this. We can also use it to explain and explore the world of work and explore some of the effects we see on our teams from, well, I'll show you, from blockages and so on. So back to following the work, or why traveling slower often makes you go faster, which is kind of counterintuitive, and why queuing for lunch at conferences suck, because I often do this at conferences, and queuing for lunch at conferences sucks, right? So I mentioned these 3 types of wait time. We've got waiting for other teams, we've got scheduling, and we've got queues. Now, I'm a big fan of this book, Principles of Product Development Flow. And Principles of Product Development Flow by Don Reinertsen. It's got something like 280 principles about how the world of work works, essentially. It's very dense, but it's brilliant, absolutely brilliant. And I'm going to talk through a few of these that might be of interest and show you some models that might help explain them or demonstrate them. So the principle of congestion collapse: when loading becomes too high, we will see a sudden and catastrophic drop in output. So if you think of this on a development team, right, you've probably all come across the point where, for some unknown reason, everyone's working really hard, like can't go any faster, can't do any more, but nothing seems to be happening. Suddenly, for some reason, work is just stuck. Right? Work is just stuck in the team. We're not deploying anything. We're not actually getting anything out. Maybe it's because a hippo, highest paid person in the room, reprioritized something at the top of the queue. So you had to reload the queue. We had to reload all our test data. We had to do all this. But for whatever reason, the team just stops getting stuff done. Now, the good news is that is just a function of teams, because teams are systems prone to congestion collapse. This is a thing that we can't avoid. If we put too much load on teams, they will slow down until gradually a phase transition occurs and everything stops. Now, you can show this using NetLogo. This is a model of a highway. Hey, you've got great traffic in Bucharest, right? So this will be interesting. This is a model of a highway, single-lane highway, and you've got a number of cars, and they can accelerate and decelerate at a certain rate, and they've got a maximum speed, right? That's what this model is. When you run the model, what you see is a phase transition to congestion collapse on the system of the highway. Right? You've all seen this. This is where there's no crash, there's no incident. It's the red light thing, right? Red lights in the distance, and then red light, stop lights on the back of the cars, and suddenly everything bunches up, and then expands again, and bunches up again. The highway's undergone congestion collapse, and it's purely a function of there being too many cars on the road for that speed limit. That's the function that predicts congestion collapse on highways. It's why, if you change the parameters, say, and follow the peak throughput principle, which is to control occupancy of the system prone to congestion collapse. It's why we have things like stoplights on ramps on motorways in the UK. We have variable speed motorways. Right? Because if you vary these initial parameters, the system comes out of that state of collapse and transitions into a steady state, as you sort of see here. I've done nothing except lower the number of cars in this, and it has this steady state. But you could do the same thing by lowering the speed limit, which we do in the UK on smart motorways. So if there's too much traffic, we'll bring the speed limit down to 50 miles an hour from 70, which improves flow. And sometimes it comes down even further to 30 if there's too many cars, and that, again, improves flow. So we can do this with our teams. We can use these ideas in our teams. This is why in Kanban, things like work in progress limits are a thing. Ooh, clapping next door, I got really worried then. I'm like, no, I've still got 15 minutes, we're all right. This is why Kanban is a thing. This is why work in progress limits in Lean is a thing, right? We say we're going to limit the amount of work in development to 4 items, right? We can't push anything more into that, right? We'll just work on these 4, or number of things that can be tested is 4. It's because we're controlling occupancy of the states in the development process, right? That's the theory behind it, essentially. But it's the same as happens on motorways. Right? They're prone to congestion collapse, and so are our teams. So the peak throughput principle, control occupancy to sustain high throughput in systems prone to congestion. Put WIP limits in. Don't just, if you're blocked on one thing, don't just pick another thing up, and then another thing up, and then another thing up. Because you'll end up with 15 things all in half-done states. Nothing progressing, the system collapses. But you can control that by using WIP limits, as an example. And the principle of alignment, there's more value created with overall alignment than the local optimization. So yes, your developers might be going very, very fast, but if you've got a huge queue of things waiting to be tested, like the overall system is under collapse. So you need to optimize the whole, not just the local. Right. The next thing is second queue size control principle. Don't control cycle time, control queue size. Ooh. I put this in here just because I like the photo, and because at some point you have to appeal to authority. And this is to prove a thing. Have you heard of Conway's Law? People have heard of Conway's Law. So Conway's Law states that the structure of the software that you build will mimic the structure of the team that builds the software. The organizational structure defines the structure of the software that's built. And I like putting this in here because, well, A, it's a laugh. B, it means I get to say I went to Anguilla in the Caribbean for work, which is pretty amazing. And C, I met Mel Conway. He's real. He's a real person. Anyway, Mel Conway. So here's another example of this. The principle, hang on a second, sorry. Sorry about that. Here's another interesting thing for this point in time. In terms of coming back to work and things, right? We've seen a lot in the UK that companies are looking at coming back to 3 days a week, going to hybrid models. And the interesting thing here is it's related to Conway's Law. Conway's Law is about communication. It's about the bandwidth of communication you have with people you're working with. The higher the bandwidth, the better it is in terms of outcomes. This is another principle from Don Reinertsen. Principle of face-to-face communication. Exploit the speed and bandwidth of face-to-face communication. Related to that is another interesting book by L. David Marquette about information and how information flows in hierarchies, right? So in organizations, we have these big hierarchies, and what we're used to doing is pushing information up the hierarchy so people can make decisions. Again, in terms of flow, it's much, much better if you push information down to the teams, to people working on those teams who've got the right amount of information to make the decisions, as opposed to pushing information up. So don't move information to authority, move authority to the information. Now, on to conferences and lunch. Did you queue for lunch? Yes, people queued for lunch, right? Most conferences you end up queuing for lunch. But the interesting thing here is about how you understand when you've got a problem with people queuing for lunch. Now, so say you've got lunch being served at 1 o'clock in the afternoon, right? You've got a bunch of people who are like in the expo or haven't gone to the last session. So they kind of, they get to go to lunch and they get to get their lunch and it's nice and quick and that. Then the sessions finish and boom, everyone else turns up for lunch, right? So you have this big queue of people waiting upstairs in a line or waiting to have lunch. And then you've got the hungry people who are afterwards who come a bit more of a steady state. And then you've got this steady rate of departures. Now the question is, if you're a conference organizer, what's the best measure to use to understand how long people are waiting for lunch? If you come across things like the DORA metrics, we often talk about lead time or cycle time, right? The cycle time from developer committing code to going into production. But the thing is with lead times and cycle times, or measuring lead time and cycle time, they're trailing indicators of whether you've got a problem. You don't actually know you've got a problem until you measure the cycle time, and you can't measure that until afterwards. Right? But there's another indicator, which is a leading indicator, which again we can use in our teams, and it's why the 2,000 entry Jira backlogs suck, right? And that's queue depth. Because there's a mathematical relationship between the number of stuff sitting in a queue waiting for something to happen and the length of time it takes to happen. It's kind of obvious when you think about it. So as an example, in this case, if we measure cycle time, a trailing indicator of problems, hungry people not having lunch yet, we're going to have to wait until 1:35 to find out we've got a problem. Because we're going to have to wait for this person to get served and depart all the way over there. But we can measure queue depth instead. If we just look at the number of people standing in front of the buffet table, we can immediately go, oh God, maybe we should have had 2 buffet tables, right? Or 3 or 4. This is what happens in supermarkets or in airlines. So when you have like one single desk open and a big queue of people turn up, in a supermarket you'll often get the ding dong, all staff to the checkouts, please. They monitor via video actually, they monitor the number of people queuing and increase the number of people's, the grocery people serving you, dependent on queue depth, not by waiting for you to leave and asking how long did it take. And we can do this, again, with our teams. If we manage our backlogs effectively, if we make sure that we don't have these 2,000 item Jira backlogs where most of it is noise, we can look at the amount of stuff waiting, and we can make really good predictions about how long it'll take before that stuff goes into production, rather than waiting for the thing to go into production and then knowing. That's another interesting little tip. The next thing is this about I should finish now, is batch size queuing, the batch size queuing principle. So batch size, queue depth, and cycle time, this is all about how we can improve throughput, again, of our teams without changing the number of people on our teams or making them work harder. So say you've got 2 batches of requirements going through into production, right? One batch here, another batch here, right? So you start earning money there, and you start earning money there. Just by reducing the batch size, deploying more frequently, which is what this means, you've got the same amount of requirements, the same amount of shaded space here, same area, but you start earning money here, 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 here. So this is another way that we can optimize the flow of work through our teams. So I've been trying to understand and explain how the world of work works, right? How stuff flows through the system of work from requirements through into production. And there's some techniques, tips we can use to optimize that, and using some interesting modeling, like using NetLogo and stuff to understand some of these characteristics of our teams. These are the principles that I talked about in the main. So principle of congestion collapse, peak throughput control principle, and second queue size principle, batch size queuing principle. All of this comes from a bunch of literature. You can read about this yourselves in these books. We've got Principles of Product Development Flow, Accelerate, Team Topologies. And I think all of that actually comes from the study of complexity science, which are these 3 books down the bottom. Now I did ask you, I'll let you go after this, what would Lego do? What would Lego do if you were in charge of Lego? What would you do to improve the system of building Lego? Sorry? Group by colors or by size, yeah, that's one option. Sorry? Yes, you could do that. Um, the interesting thing, when I started building Lego as a kid, you used to get a Lego set, and it was all just blocks in one place, right? Just all blocks in a bag or whatever, and you had to find them all, and you could group them by size and color. So what Lego did is exactly that, right? So these days, what happens is you get a bag per 10 pages of the book, and all the stuff you need is there. Essentially, Lego reduces batch sizes. So if the best way that Lego can work out how to build Lego is by reducing batch sizes, that's probably the best thing we can do on our teams to improve throughput. By halving batches, we double throughput. That's the relationship. So that's what you want to take away. Cool, and that's me. Thank you very much.